Hello, everyone. Welcome to our QPL talk. I'm joined by my co-authors, Martti and Rui, who are going to speak a little later. And we're delighted to be able to present our paper virtually at QPL. Very much looking forward to being able to meet up with the QPL community in person in the near future. The paper that we're going to talk about today has appeared recently on the archive about a month ago. So you can find it there. It was originally prepared as a contribution to a volume of Springer's Outstanding Contributions to Logic series, dedicated to the work of Samson Abramsky. And indeed, the research that we're going to talk about today builds on some work that we've been doing with Samson over the past number of years on contextuality and, in particular, resource theories of contextuality. So, to give an overview of what's coming today, let's start with the notion of contextuality. In a nutshell, we could say that contextuality is the quintessential marker of non-classicality. So it's an empirical phenomenon, something that we can observe in experiments, which distinguishes the behaviors of quantum systems behaving according to the laws of quantum mechanics, from classical systems behaving according to the laws of classical physics. So it's very much studied today as a useful resource that can confer quantum advantage in a variety of informatic tasks. We know it to be necessary and sufficient in a number of situations. The resource-theoretic perspective that we have taken with Samson, and you can find our resource theory of contextuality in a LIX paper from a couple of years ago, it shifts the focus from objects to morphisms. So objects in this case being the empirical data itself, formalized as an empirical model of a particular type. So we write an empirical model of type S, where S is the kind of experiment that we're talking about. And it moves from objects to morphisms, where we're really talking about which empirical behaviors can be converted into others. So we write things like D simulates E to denote a simulation of an empirical model of one type using an empirical model of another type. I think they could be the same type, I guess, in general. These simulations arise as free operations, which are given by classical procedures on the experimental setups themselves. So these are transformations of the types. And just to note that in this particular talk, we're going to focus only on non-adaptive procedures. This is a restriction that we make here and applies to the results that we're going to present. But note that the general resource theory of contextuality that we have set up with Samson previously in our LIX paper can perfectly well handle the adaptive procedures as well. So the question that we set out to answer is this one. Given all of the empirical models of type S as a set, and all of the empirical models of type T as a set, we can consider maps between them. And we're going to ask the question, which of all of these possible maps arise from classical procedures? So to outline how we go about answering this question, we're going to construct a new kind of scenario, experimental scenario, denoted square brackets ST. And we're going to represent a map between these sets of empirical models as an empirical model itself. Now, once we represent something as an empirical model, a natural question arises, is it contextual or not? And this, it turns out, is the key to answering our question. So these maps are realizable by classical procedures if and only if this new description of the map as an empirical model turns out to be non-contextual. there are some caveats about this, which we'll get to later. Also, let me mention that this square bracket provides a closed structure on the category of measurement scenarios and classical procedures. So contextuality, just back to basics. We're going to treat experiments as black boxes, essentially. And so we're going to think of them as black boxes with some buttons that we can press, and we've got some output displays that will display as an outcome. So anytime we interact with a system, we're going to think we're performing measurements on it, and we're obtaining and observing the respective outcomes to those measurements. So for instance, if I push the green button on this box, I'm going to observe some outcome. The pointer deflects to the right, so we can interpret that as a 1. If it deflects to the left as a 0, for example. Something about these black boxes is that we're often dealing with a non-trivial compatibility structure on the measurements. That is to say, there are certain combinations of measurements that we can make together and certain combinations that we can't. In this picture, that means some of the buttons can be pressed at once, but some combinations are not allowed. So, for instance, I could press a blue button and a green button together, obtain some outcomes, or I could press a green button and a red button together and obtain some outcomes. But the compatibility structure that we've represented here as a graph where the edges denote compatibilities. More generally, this could be a hypergraph, of course, but here we've got pairs of measurements being our maximal compatible sets. So here, some combinations are forbidden. All 3 buttons would not be allowed. So that's a situation that is not permitted. So this compatibility structure is something that comes with the box. It's part of our description of the kind of experiment that we're talking about. So this is what can be formalized as a measurement scenario. If you take the Abramsky-Brandenberger approach to talking about empirical data and ultimately contextuality, here we're representing in black box language. So that's the kind of experiment that we're talking about. So knowing the box, the buttons that it has, their compatibilities, and which outcomes we might be able to observe from these, that describes the kind of box or the kind of experiment, the type that we're dealing with. But the behavior itself is something more. So the behavior of the system is described statistically. So we can tabulate this. That would be one way of representing it. For instance, if we press the blue and green buttons, we'll observe some outcomes. If we do this a great many times, we can observe some frequencies. Or if we have a theory that predicts how the box is going to behave, we can just consult that. So in this case, let's say 3/8 of the time, we observe that the blue button and green button result in deflections to the left and to the left. And with some other probability, 1/8, we get a deflection to the left and one to the right, and so on. And we can just complete this table where we measure the blue button and we press the blue button and the red button. We get some other set of probabilities and so on. So these statistics are what we can formalize as an empirical model. It's really just a collection of probability distributions, one for each context of compatible measurements. There's a feature of empirical models that we're interested in. It's a feature of all empirical models that arise from classical physics or quantum physics, and it's called no signaling. Sometimes it's referred to as no disturbance in the more general case. And what that requires is that marginal distributions should agree. So, for instance, I could measure green together with blue, but I could also measure green together with red. So let's start. If I measure green together with blue, let's suppose I forget what happens with blue. Forgetting, I can describe that just as marginalization. So I marginalize the probability distribution. That's to say, I just sum over the outcomes of the blue measurement. And that would give me some probability distribution for what I should see with green. On the other hand, I could have measured green together with red, forget the red outcome, and see what probabilities that leads me to find for the green measurement. If the marginals agree, then that allows me to, in a well-defined way, talk about just the probability of various outcomes for green on its own. So it allows me to talk about, in a well-defined way, this particular probability. Okay, so that's something that's built into our empirical models. Now we'd like to get around to talking about contextuality. And contextuality, it's something about how we can or cannot model what's happening inside this black box. So we attempt to put a classical understanding or a classical picture inside this box. And at the basic level, the classical picture would be a deterministic model. So a deterministic model is that, okay, inside this box, there are just instructions that say that, yep, whenever green is pressed, you're going to result in this deflection to the right, for example. Whenever blue is pressed, you're going to result in this deflection to the left, for example. So if I press these buttons, the box just looks up what it's supposed to do and sends out those outcomes. So that would be a deterministic model. We can allow something a little bit more general, classically, to obtain probabilistic behaviors. And so that's to just introduce some randomness. So yes, we have these pre-defined values that are fixed inside of the box, but maybe there's like the roll of a dice, and with the depending on the roll of the dice, it could be one set of predefined values or another set of predefined values. So that's something that we allow in a classical description. And so any behavior that we can model in this way, we call it non-contextual. So this is a way of formalizing what we consider to be classical behaviors. If we cannot model a behavior in this way, we say we have a contextual model.
So we now move on to talking about the resource theory of contextuality. And the idea behind resource theories is that we're no longer interested in studying just systems of a given type or behaviors in a given fixed measurement scenario, but rather we're interested in procedures that transform boxes of a given type S into boxes of another type T. And in the running examples that we'll consider here, we'll consider the same boxes, the same type of boxes S that Shane was talking about, and we're considering procedures that transform such boxes into boxes of a new type T, which has full measurements and is particularly compatible with the structure we're presenting. So, but in general, what we're interested in is in characterizing what are the free or classical operations, i.e. the operations that do not require any the consumption of our resource of interest, in this case, contextuality. And so what these are classical procedures that use a box of type S in order to simulate a box of this other type T. So the first ingredient in defining the kind of procedures or that constitute the free operations in our resource theory of contextuality is the notion of an experiment. So an S experiment is essentially a protocol for an interaction with the box S. So this has to specify two things. So the first of them is which measurements we're going to perform. And secondly, how do we interpret their joint outcome into an outcome of the intended type for our experiment. So here is an example. And let's imagine, so we have this little lab book that's making a description of this particular protocol, and here is the experiment that's going to follow this protocol. And what they're going to do is basically perform, so in this case, we're going to perform two measurements, the green and the blue measurements. They observe an outcome for each of these measurements, and then they have some way, so the protocol specifies some way for them to combine these joint outcomes into an outcome of the intended type. So given this notion of experiment, what a deterministic procedure from S to T in order to transform a box of type S into a box of type T. Essentially what it does is to specify an S experiment for each measurement of T. And there's a slight caveat that we'll get to in the next slide in order to define which of these choices of S experiments are valid. And then let me just add that so here's an example of one such deterministic procedure. And then so lastly, a classical procedure from S to T would just be a convex combination of such deterministic procedures here represented by these dice. So let's see. So if we have this notion of a classical procedure for transforming a box of type S into a box of type T, let's see how that actually allows us to simulate a behavior of a box of type T given a box of type S with a certain behavior. So here's an example. Let's imagine that we press the pink button, so we try to perform the pink measurement on T, and what actually happens is that you can imagine there's an experiment inside this box that will look at the corresponding experimental procedure and perform that. So in this case, we're going to perform the measurements. The green measurement observes some outcome and then transform that into an outcome of the correct side for T. And similarly, imagine this is, for example, the protocol for when the red measurement is pressed. But then there's also, it might also happen because the pink and red measurements are compatible in T that we try to measure both at the same time. And so the protocol this protocol has to have a way of reacting to that. And the idea is that both of the experiments run in parallel without interfering with each other. So here there are the two experimenters sort of performing the one corresponding to pink and the one corresponding to red simultaneously or in parallel. However, note, and here's a slight caveat. So let's imagine that the experiment that's specified for the measurements, the orange measurements, is the following: is that one is supposed to measure both the green and the blue button, the green and the blue measurements in S. And if that's the case, so it could happen that the orange and the red measurements are both performed at the same time because they're compatible measurements in T. And in that case, we might run into a problem because the red measurement is asking us to perform the brown measurement of S, whereas the orange measurement of T is asking us to perform both the green and the blue measurement in S. And we know that the compatibility structure of S forbids these three measurements being performed. So in fact, these two protocols, the red and the orange protocol, cannot be run in parallel. So they cannot be run at the same time without and leading to a valid use of the box S. So in fact, the notion of a deterministic procedure and consequently of a classical procedure has this extra constraint that the protocols that are chosen have to, for jointly compatible measurements in T have to be jointly performable in the sense that performing them together wouldn't violate the compatibility structure of S. Right. So now that we have these classical procedures, as we've just seen, so if you have a classical procedure that specifies how to transform a box S into a box T, this induces a map between empirical models of S, or behaviors of box X, and behaviors of a box T, or empirical models of T, as we've just seen in the previous slide. And this is, moreover, a convex preserving map between empirical models. So it preserves convex combinations. So the question that we set out to answer is which black box transformations arise in this fashion. So given a classical procedure, we get one such transformation from empirical models of S to empirical models of T, and the question is which such transformations arise from classical procedures. So here we have. So if we're given one such f one such function from the empirical models of S to empirical models of T, here represented by the blacked out factory, so we don't know what's going inside. It can be any such function. The question is, can it be realized by an experimental procedure? So is there an experimental procedure from a classical procedure from S to T such that this function f is the corresponding simulation, the corresponding map between empirical models? And one immediate answer, so one immediate partial answer that we have is that we know that this map F has to be convex preserving, and from now on we're going to assume that. But in between convex preserving maps, we're trying to characterize which ones do arise as classical procedures, or which ones are realized by classical procedures. So let us first just make an observation, and let's specify this question to the particular special case where S is the box I. And what I mean by the box I is the box that has no measurements. And therefore, if it has no measurements, it has, there's no possible interaction that we can have with it, or the only interaction that we can have with it is the empty interaction where no measurement is performed and therefore no outcome is observed. And therefore, there's a single empirical model. So this box is a single empirical model, which is given that there's nothing to specify in how we can react to interactions. And so let's now look at this question now specified for the box I, and look at both sides of this question mark equation and try to simplify and see what it simplifies to. And as I said, so the empirical models of I is a single empirical model. And we also know that a function from a singleton set into any other set is just an element of that set. So what we have on the left is basically just a chosen empirical model or a chosen behavior of the box T. Now, what about to right? Then it's also easy to see that if we have these protocols for interacting with I and then getting post-processing the outcomes into an outcome of the right type for T, then what this is basically going to be just a choice of such an outcome, given that there's no possible interaction with this box I. So therefore, what we have on the right is just a deterministic invariable model or a non-contextual invariable model. So essentially, the question that we set out to answer when we specialize it to the case where S is this trivial box I, it reduces to sort of this more well-studied and well-known question, which is given an empirical model or behavior of a certain type, an empirical model in a given measurement scenario, is it or is it not contextual? And just another way of saying that is that the non-contextual models are exactly those that can be simulated from nothing. So, sanity check that this is actually the right resource theory for contextuality. So, one way of reading what we've just said is that we had this question that is well studied in the literature of contextuality, which is given an empirical model, is it or is it not contextual? And we've generalized this to, so it is a special case of a more general question, which is kind of a relativized question, which goes from objects to morphisms, goes from studying single systems to transformations between systems. Then it becomes this question, which is given one of these maps between empirical models, can it be realized by a classical procedure? And what turns out to be perhaps somewhat surprising, so the answer turns out to be that we end up reducing this more general question to the original, more specialized case in some sort of internalization of this question. So let me just give a brief account of how this goes. So the idea is the following. If we're given two scenarios, or two types of black boxes, S and T, we'll build a new scenario, which you're going to call HOM of ST. And we'll give some more details of what it is. But the idea is then the following, is that given any convex preserving map that maps empirical models of S into empirical models of T, so any convex preserving function between behaviors of S and behaviors of T, this gives rise canonically to an empirical model or to a behavior of this new box that we've just built, the box HOM of ST. And moreover, the original function f between empirical models of S and empirical models of T turns out to be realized by a deterministic procedure if and only if this canonical model we've just constructed is a deterministic model. And moreover, by taking convex combinations in both cases, it turns out to be realized by a classical procedure if and only if this constructed model is non-contextual. So in fact, there's a slight caveat that we should add to this, which is that additionally, this empirical model has to satisfy what we call predicates. And what a predicate is so one way of explaining what a predicate is, or of defining it in our resource theory, is that it is just a classical procedure from a given box into the box that we call 2, which is the box that has a single measurement and 2 possible outcomes, let's say false and true. And we say that the particular empirical model satisfies that predicate when the image under this procedure of that empirical model gives rise to the empirical model that always outputs with 100% probability the output true. And if you've seen this before, so one way of thinking about these predicates is as a specification of a non-local game, or more general contextual game. And to say that an empirical model satisfies it is essentially to say that it is a perfect strategy for that game.
So let's elaborate a bit more on some technical details. So to start with, let's talk about this home scenario that we build out of the scenarios S and T. So its measurements are exactly those of T, and the compatibility structure is exactly the same as in T as well. And an outcome at some measurement X of T is basically an S experiment. So it tells us what to measure in S and how to interpret such an outcome as an outcome of X. And now this specifies the scenario completely, because we've told what the measurements are, what the compatibility structures is, and what the outcomes are. But we'd also like to enforce that take into account the compatibility structure of S somehow. Namely, if you ask a compatible set of questions of T, then you get some instruction sets. But these instruction sets only make sense together when they end up asking a compatible set of questions of S. And the way to take that into account is to not just take this scenario, but also take into account a predicate, so a sort of non-local game that checks for each context of T that you're only measuring a compatible part of S. And now if you take those into account, then this scenario really behaves kind of like an internal home. So for example, if you look at deterministic models that satisfy this predicate, then those are exactly the deterministic procedures from S to T. And thus, if you take a classical procedure, so a mixture of deterministic procedures, then those give you the non-contextual models over this home scenario. And one way of getting intuition into this is by looking at this evaluation map. The reason why I have square quotes here is because this doesn't quite make this into a monoidal closed category. But let's ignore that for the moment. And similarly, this evaluation map goes a bit beyond what we've worked with so far because it's adaptive. So let me just explain how it works, and hopefully it will become clear. So the idea is that if we have both of these boxes, so a box of type S and this home scenario from S to T, then we can simulate a copy of a box of type T. And the way it works is, well, if you have to measure something in T, well, that corresponds to a measurement in the home scenario. So you measure that corresponding scenario, you get some outcomes, and these outcomes tell you what to measure in S. So you go and do the corresponding measurement in S, you get some outcomes, and then you look again at your instruction set, and this instruction set tells you how to interpret those outcomes as measurements in T, and finally you output those in T. And in this way, having both of these boxes lets you pretend you have a copy of T. Okay, and now we can say a bit more about the inner workings of the proof. So two key lemmas that, were already known, but we use here are the following ones. So first of all, even if you take a contextual empirical model, well, it's always going to be a affine mixture of deterministic models. So the important thing is that these affine mixtures allow us to also have negative coefficients instead of just non-negative coefficients. And in this way, this is actually the way negative probabilities come into play in quantum mechanics. And the other aspect is that if you take any function that preserves all the convex combinations here, it will also preserve automatically all the existing affine combinations. And it immediately follows from these two that if you take a function defined on empirical models over S, then it's determined by its restriction to the deterministic models on S. On the other hand, if you look at these distributions on an n-element set, well, those correspond exactly to empirical models on a scenario with exactly one measurement and n outcomes. So then if you look at functions from the deterministic models on S to such probability distributions here, well, that's the same thing as a convex mixture of ordinary functions from S to an n-element set. And a key lemma that we observed in this work, it's probably known elsewhere, but we haven't sourced where to find this, is that if you take any function defined out of defined on the deterministic models, then there always is a unique smallest subset of measurements that you need to measure, so that knowing the value of the deterministic model on those measurements is enough for you to know the outcome, the value of this function f. So now if you have a deterministic function like this, well, then such a thing comes from a deterministic experiment with n values if and only if the smallest subset of measurements that we need to measure is a compatible set of measurements in S. And as a result, if you take a convex mixture of these things, then it comes from an experiment precisely if each of these smallest subsets comes from a jointly compatible set of measurements. And now we can explain how the answer works more generally. So if you take any function that preserves convex combinations between sets of empirical models, it's again determined by what it does on deterministic models. And now if you take any compatible set of measurements in T, you then get a mixture of these deterministic functions from deterministic models on S to joint outcomes. And for each of those functions, you can replace it by one that measures the least amount of S possible. And now we've defined for each context of T, so each jointly possible measurement of T, some probability distributions, and these always glue together to an empirical model on the home scenario that we just talked about. And then the main theorem is that this function f comes from a classical procedure from S to T, if and only if this empirical model that we build out of it is non-contextual and also satisfies this predicate that checks that we only ask compatible questions out of S. And one further upshot of this result is that it makes you think that, okay, the basic objects of the theory, maybe they shouldn't just be, or the basic types shouldn't just be these scenarios, but they should be pairs of a scenario equipped with a predicate that restricts you to sort of the relevant empirical models on that scenario. And then a map between two such pairs is just a procedure between the underlying scenarios that preserves sort of satisfaction of this predicate. So if you take a model over S that satisfies this predicate G, then its image in T should also satisfy the structure predicate of T. And now if you work in this category, then the internal home construction, where you now take into account the structure predicates, makes this category into a closed category. And here, when I say closed category, I don't want to explain in detail what that means, but that's roughly a category with an internal home. And that's kind of like a monoidal closed category, except that we don't assume that we have a monoidal structure that cooperates with these internal homes. We just have this closed structure. And now this leads into some further questions. So first of all, we restricted our attention to only the non-adaptive procedures, whereas in other work before we've looked at more general adaptive procedures, where you might first measure something in S, and then based on the outcome, you might choose what to measure next, and then based on those outcomes, you choose what to measure next, and so on. And now you can still build an adaptive version of this home scenario just fine. The trouble is that there's one of the key lemmas breaks down, and there's no obvious way of building a canonical empirical model on the home scenario out of a function between sets of empirical models. But perhaps there is some way of making the similar kind of proof and result work, but we haven't yet figured out how that works. Another aspect is that instead of just empirical models, people often care about possibilistic empirical models, where you only remember whether our joint outcome is possible or not. And if you try to do the same, so instead of functions between sets of empirical models, you look at functions between sets of possibilistic empirical models. Again, the previous argument breaks down because there's no obvious reason why you can restrict to just the deterministic models, but perhaps there is some tricks that still let you get a similar kind of result work there. We just don't know how to do that yet. Another aspect is that these predicates themselves should be taken seriously. So in particular, if you look at all predicates on a fixed scenario, they kind of look like a Boolean algebra, except that you can only do these Boolean operations for predicates that sort of ask questions in the same context. And that's kind of like a partial Boolean algebra, except that it's defined on an arbitrary measurement compatibility structure instead of just on a graph. And that's something we should look into. And so finally, we should make sense of this closed structure. So together with the evaluation map, it almost looks like a monoidal closed structure, but it isn't. And the reason is that this sort of, if you already look at the evaluation map, it sort of first measures things in the home scenario, and then it proceeds to the other scenario and never returns. Whereas a general measurement protocol, so an adaptive procedure on a tensor product, might ask something in one scenario, then go to the other, and then come back and keep bouncing. Whereas it seems like we somehow need to build a framework where the tensor product is sort of directed in a way that measurement protocols only start from one, and then they always move to the other one without ever returning. And if all of that was made to work somehow, then we'd expect to get the monoidal closed category. And that's something we should figure out. And now, if you have any questions about this work, please ask us. We'll be around at QPL, and we'll be happy to answer any questions you may have. Thanks.